Hello, welcome back to KO Math. Today I'm excited to share with you some strategies and tricks that will let you evaluate integrals of rational functions easily. Here, I assume that you know already how to determine the correct form of partial fraction decomposition or partial fraction expansion when given an improper rational expression. Let's get started. Here's tip number one. Before you start doing partial fraction decomposition, check first whether you can apply U substitution to evaluate the integral. For example, let's say you're evaluating this integral. So we see here that this is a proper rational function. So therefore, you might think immediately that you have to apply partial fraction decomposition to evaluate the integral. But actually, in this case, when you expand the denominator, you'll get x cubed plus a 3x. And the derivative of this is just 3x squared plus a 3, which is just a constant multiple of x squared plus 1. So therefore, if this is our u, then the du will be just 3 times this numerator, which is x squared plus 1. So we can write this integral as 1/3 of 3 times x squared plus 1 all over x cubed plus a 3x dx. And by substitution, we can write it as 1/3 integral of du over u. So our u is x cubed plus a 3x. And we can easily anti-differentiate this 1 over u, and we'll get 1/3 ln of absolute value of u plus c. And putting back u in terms of x, we'll get 1/3 ln of absolute value of x cubed plus a 3x plus c. Another example, so if we're given this integral, before we apply partial fraction decomposition, we try first again u substitution. And for this given integral, if you let this x cubed to be your du is just a 3x squared dx, which is just a constant multiple of this x squared dx. So therefore, we can write this integral as 1/3 of this integral, and letting this x cubed to be our u, we can write it down as 1/3 integral of du over u minus 1 times the quantity u plus 1, which is actually a simpler rational function in terms of u. And we can actually write this denominator as u squared minus 1, and we already have a formula for integral of du over u squared minus 1. We have this formula integral of du over u squared minus a squared, which is equal to 1 over 2a ln of absolute value of u minus a all over u plus a plus c. And if you don't know this formula, of course, if you know how to do integration by partial fraction, you can also obtain this answer, which is equal to 1/2 ln of absolute value of u minus 1 all over u plus 1 plus c. So therefore, the final answer here is 1 over 6 ln of u is equal to x cubed, so that is x cubed minus 1 all over x cubed plus 1 plus c. Now, let us consider integrals where the integrand has distinct linear factors in the denominator. In this case, the best strategy to evaluate the integral is using this cover-up technique. You might be familiar with this technique already. So let us first consider the case wherein the integrand is a proper rational function. So when we say proper, in this case, the degree of the numerator is less than the degree of the denominator. So for example, we're evaluating this integral. This is a proper rational function because the degree of the numerator is 2, the degree of the denominator is 3, and we have here distinct linear factors. We have x, x minus 1, and then x plus 1. And we know that the partial fraction decomposition of this rational function is given by a over x plus b over x minus 1 plus c over x plus 1, where a, b, and c are real constants. So to find this a, b, and c, we use what we call cover-up technique. So here, if you want to find, let's say, the a, so just cover this x in the integrand. So it's like you have this expression without the x in the denominator and evaluate it at the value of x that will make this x equal to 0. In this case, it is only x equal to 0. So when we plug in x equals 0 in this expression, we'll get negative 2 over negative 1 times 1. So that is negative 1, negative 2 over negative 1. It is equal to positive 2. So therefore, this is equal to 2 over x. Now, to find this constant b, again, we cover this x minus 1 in this integrand. So it's like you have this expression and you evaluate it at the x that will make this linear factor equal to 0. So that is x equal to 1. So when we plug in x equals 1 to this expression, we'll get 1 squared minus 2, so that is negative 3 over 1 times 2, so that is over 2. So therefore, b is negative 3 halves. And our c, to find this constant c, we cover this x plus 1 in this integrand. So we'll get this expression and evaluate it at the x that will make this x plus 1 equal to 0, which is x equal to negative 1. So we'll get here 1 plus 2 minus 2, you'll get 1, all over negative 1 times negative 2, so that is positive 2. So therefore, c is equal to 1 half, and we'll get this expression. And this can be easily integrated. So the integral will be 2 ln of absolute value of x minus 3 halves ln of absolute value of x minus 1 plus 1 half ln of absolute value of x plus 1 plus c. And using a property of ln, you may write this expression as in terms of a single ln. So you have here 1 half ln of absolute value of x raised to 4 times the quantity x plus 1 all over x minus 1 quantity cube plus c. And you may actually put the constant c inside because a real number can be written as ln of another real number. Next, integral. So pause this video if you want to try this out first. So we want here to integrate this x squared minus 3x plus 1 all over 2x times the quantity 3x minus 1 times the quantity x plus 2. So we have here again distinct linear factors, 2x and then 3x minus 1 and then x plus 2. So we can use the cover-up technique. So, of course, the partial fraction decomposition of this one, this is a proper rational function. We can write it as a constant over 2x plus another constant over 3x minus 1 plus a constant c over x plus 2. And to find this a, b, c using cover-up technique, so if you want to find this a, in the numerator of this fraction with denominator 2x. So we cover this 2x in our integrand, so we'll get this expression, and we plug in the x value that will make it 0, so that is x equals 0, and we'll get here 1 over negative 1 times 2, so that is negative 1 half. And then to find this constant b, we cover this 3x minus 1 in the integrand, we'll get this expression, and we evaluate it at the x value that will make this 0, which is equal to 1/3. So by plugging in this x equals 1/3, we'll get 1 over 9 minus 1 plus 1, and then this is 2 over 3, and then times 1/3 plus 2, so that is 7 over 3. So this is equal to just 1 over 9 over 14 over 9, which is equal to 1 over 14. And then for this c here, to find this c using cover-up technique, so we cover the x plus 2 in our integrand, we'll get here this expression, and we plug in the x value that will make this 0, so that is x equals negative 2. We'll get 4 plus 6 plus 1 all over 2 times negative 2, so that is negative 4 times negative 7. We'll get 11 over 28. So now, if we'll get this a, b, c here, we can easily find the integral of this. Okay, so here it is just equal to negative 1/4 ln of absolute value of x. And to integrate this one, you use substitution. If this is your u, okay, your u is equal to 3x minus 1, your du will be 3 times dx. So its integral will be 1 over 42 ln, that is 1 over 14 times 1/3 ln of u. Your u is equal to 3x minus 1. And then plus 11 over 28 ln of absolute value of x plus 2 plus c. Now, what if the integrand is an improper rational function? When we say improper rational function, it's a rational function wherein the numerator has a degree that is equal or greater than the degree of the denominator. So, for example, this rational function. So the degree of the numerator is 4, degree of the denominator is 3. So this is an improper rational function. And in this case, you cannot use immediately partial fraction decomposition because you can only use that one for proper rational function, only for rational functions wherein the degree of the numerator is less than the degree of the denominator. So the strategy for improper rational function is to perform first long division before using cover-up technique. So in this case, this is long division. We divide this numerator by this divisor or denominator, and we'll get here 3x raised to 4 divided by x cubed. We'll get a 3x. And we multiply the entire divisor by a 3x, you'll get a 3x raised to 4 minus 3x squared. So here I aligned like terms. And then we subtract the entire product from the dividend to obtain a new dividend. And we'll get here x cubed plus x squared minus a 3x minus 2. And then we perform the same process. So we divide the leading term by this leading term of the divisor, we'll get 1. Multiply the entire divisor by 1, you'll get x cubed minus x, and then subtract this product from this new dividend, and you'll get here x squared minus 2x minus 2, and we stop here because the degree of this is less than the degree of the divisor. So therefore, this fraction can be written as the quotient 3x plus 1 plus this remainder x squared minus 2x minus 2 all over the divisor, which is equal to x cubed minus x. And we can easily integrate this one, which is equal to 3 halves x squared plus integral of 1 is just x, and the integral of this, okay, we found the integral of this a while ago, okay, so this is just 1 half ln of absolute value x raised to 4 times the quantity x plus 1 all over the cube of x minus 1, and then plus the arbitrary constant c. Next, let us consider integrals with integrand of the form 1 over ax squared plus bx plus c. So here a is not equal to 0, and the capital D here is the discriminant of this quadratic expression, which is b squared minus 4ac. And for this case, we have the case where the discriminant is equal to 0. It means that the quadratic equation ax squared plus bx plus c equals 0 has a single real root. Okay, so in this case, the strategy is to just use u substitution, because if the discriminant is equal to 0, it means that this quadratic expression is a square of a linear function. For example, if you're given this integral of 1 over 4x squared minus 12x plus 9 dx, when we factor the denominator, we'll get 2x minus a 3 quantity squared. Since this is a square of a linear function, for sure the discriminant here will be equal to 0, because as you can see, there is only one zero of this quadratic expression, and that is x equal to 3 halves. So here we can evaluate this integral by substitution. We can write it as 1 half integral of this 2x minus a 3 raised to negative 2. And then this is our u, the 2x minus a 3. So if this is our u, our du will be 2 dx. That's the reason why we multiplied here 1 half to make these two expressions equal. And then now just think of this as integral of u raised to negative 2 du. So its integral is equal to u raised to negative 1 over negative 1 plus c. And we can simplify this, write it down as 1 over, this is 2x minus 3 times negative 2, you'll get 6 minus 4x, and then plus the arbitrary constant c. Now, let us consider integrals where the integrand is of the form y over ax squared plus bx plus c. Again, a is not equal to 0 and the discriminant is positive. So, first strategy, if you know that the roots are negative b plus minus square root of d all over 2a, then you can use actually this integration formula to evaluate this integral quickly. It is 1 over the square root of d, square root of the discriminant, ln of absolute value of x minus root 1 over x minus root 2, where in this case r1 is greater than r2. So, for example, if you have integral of dx over 2x squared minus 5x minus 3, the discriminant here is negative 5 squared minus 4 times 2 times negative 3, which is just 25, and then plus 24, so that is equal to 49. So it is greater than 0, so we can use this technique. Then the value of this integral is just 1 over square root of d, which is 1 over 7, and then ln of what are the roots? So since this is factorable, it's very easy to find the roots. So the roots are negative 1/2 and positive 3. So the higher root goes to the numerator and the smaller root goes to the denominator. So you have here x minus 3 all over x plus 1/2. Actually, we can write this expression as 1 over 7 ln of absolute value of x minus 3 all over 2x plus 1. It's like multiplying this denominator by 2. But of course, we have here a constant which is different from this constant c. So here we have this c sub 1 as actually 1 over 7 ln of 2 plus c. And if you're going to use property of ln, this is 1 over 7 ln of this expression plus ln2. So it will be ln of the product and you'll get the denominator, which is x plus 1/2. Now, if you see this expression, so also this is a technique in finding the integral of this expression if you know the factorization of this ax squared plus bx plus c, because x minus 3 and 2x plus 1 are just the factors of the denominator. So actually this will be 1 over square root of d, and the numerator here is just the factor that will give you the larger root, which is in this case it's 3. And the denominator is the factor that will give you the smaller root. In this case, the smaller root is negative 1/2. Let's have another example. Suppose we want to integrate this one, integral of dx over 2x squared minus 4x plus 1. Now, if we look for the roots of this equation, expression equal to 0, then the root will be equal to, again, negative b, so that is 4, plus minus square root of b squared, which is 16, minus 4 times 2 times 1, 4ac, which is 8. So this is square root of 8, and that is our square root of d. Okay, so this one, it is equal to 4 plus minus 2 root 2 all over 4, and we can write it as 2 plus minus square root of 2 all over 2. So using this formula, integration formula, the integral of this is just 1 over root d, so root of 8, square root of 8, and then ln of absolute value of x minus the larger root. Of course, the larger root will be 2 plus square root of 2 all over 2 all over x minus the smaller root, which is 2 minus square root of 2 all over 2. And then plus the arbitrary constant c, and we can write it in this form. So 1 over 2 square root of 2 ln of multiplying the numerator and denominator by 2 will get this expression. Another strategy to evaluate the integral is using by completing the square. So here we were given this integral of dx over 2x squared minus 4x plus 1. So we can evaluate this integral in the following way by completing the square. So first, it's very easy to complete the square if the coefficient of x squared is 1. So therefore, factor out first 1/2 here, and you'll get integral of dx over x squared minus 2x plus 1/2. And you complete this one, x squared minus 2x. And how do you get the constant that you're going to add to this binomial to get a perfect square trinomial? You divide this negative 2 by 2 and you square it. So negative 2 divided by 2 is negative 1. You square it, you'll get 1. Okay, so make sure that this expression is equal to this x squared minus 2x plus 1/2. You have here plus 1, so to make it 1/2, you subtract 1/2. So now this is already a perfect square trinomial. You can write it down as x minus 1 quantity squared, and 1/2 can be written as the square root of 2 over 2. So that is square root of 1/2, right? So when you square this, you'll get 2 over 4, which is equal to 1/2. So this is already in the form integral of dx over u squared. It's like du over u squared minus a squared, and we already have a formula for such an integral. And using this formula, so we have 1 over 2a, so our a here is just square root of 2 over 2, so 2 times this. Square root of 2 over 2 will just get square root of 2. So it will be 1/2. So 1 over 2 square root of 2, ln of absolute value of u, which is x minus 1, minus a, all over u plus a, and then plus the arbitrary constant c. And again, if we multiply the numerator and denominator by 2, we'll get this expression, and then plus c. So this is the same expression that we got a while ago. Now let us consider integrand of the form 1 over ax squared plus bx plus c. Again, a is not equal to 0, but the discriminant in this case is less than 0. So that means the equation ax squared plus bx plus c equals 0 has two imaginary roots. Okay, so in this case, the fast way to evaluate the integral is using this formula. So integral of 1 over ax squared plus bx plus c dx is just equal to 2 over square root of absolute value of d, and then tangent inverse of the quantity 2ax plus b all over square root of absolute value of d, and then plus c. So this is easy to remember because you have here the 2, and then you have here the 2, and then square root of absolute value of d, square root of absolute value of d. And actually the numerator here is just the derivative of the denominator with respect to x. So when we differentiate this, we'll get 2ax plus b. So, for example, if we're going to integrate dx over 2x squared minus 3x plus 4, so when we compute for the discriminant, we'll get here b squared, which is 9, and then minus 4 times 2 times 4, so that is minus 32. We'll get negative 23, which is less than 0. So we can apply this strategy. And this is the fastest way to evaluate this integral. So we'll get here 2 over the square root of the absolute value of this, which is 23, tangent inverse of the derivative of this denominator, which is just 4x minus 3, all over the square root of 23, and then plus c. We may also evaluate the integral by completing the square. So here, if we evaluate this integral by completing the square, again, we first factor out 1/2 to make the coefficient of x squared equal to 1. It's easier to complete the square. So you'll get here x squared minus 3/2 x plus 2. And then to get the constant that you're going to add to this binomial to make it a perfect square trinomial, just divide this negative 3/2 by 2. You'll get negative 3/4, and you square it, you'll get 9 over 16. Now, we need to add 23 over 16 to get the plus 2 here. Okay, so you have 9 plus 23 is 32 over 16. It is only plus 2. So this expression is equal to this expression. Now we can write down the denominator as the square of x minus 3 fourths, and then plus this one as the square root of 23 over 4. And using our integration formula, integral of du over u squared plus a squared equal to 1 over a tangent inverse of u over a plus c. So we'll get here 1 half times 1 over a. Our a is square root of 23 over 4. Tangent inverse of our u is just x minus 3 halves all over square root of 23 over 4 and then plus c, which can be simplified as 2 over square root of 23 tangent inverse of the quantity 4x minus 3 all over square root of 23 plus c, which is actually the same expression as what we got here using this faster technique. Now let us consider integrals with integrand of the form rx plus s all over ax squared plus bx plus c. So the strategy here is to write it as a sum of two fractions, and the first fraction will have a numerator which is just a constant multiple of the derivative of the denominator. So it is constant times 2ax plus b. Because in this case, we want to use substitution to evaluate the integral of this expression, and we've learned already how to evaluate this integral. So here, if you're given integral of 2x minus 5, so this is, you have here the dx, of course, okay, all over x squared plus 3. So we can write it down as, again, the derivative of this one is just 2x, which is exactly the same as this one. So we can write it as the integral of this expression minus 5 integral of 1 over x squared plus 3 dx. And to evaluate this first integral, we just use u substitution. So if the denominator is our u, this 2x dx is just our du, so integral of du over u is ln absolute value of u. But in this case, the u, which is x squared plus 3, is always greater than 0, so we ignore the absolute value and just replace it by a grouping symbol. And to evaluate the second integral, we use this integration formula, which is 1 over a. Our a here is square root of 3, so 3 is the square of square root of 3, so that is 5 over a. And then tangent inverse of u, our u is just x, over a and then plus c. Let's have one more problem. So pause this video if you want to try this out first. So let's evaluate the integral of 8x minus 5 all over 2x squared minus 3x plus 4 dx. So again here, so the technique is to write it as two integrals. So here we have 2x squared minus 3x plus 4. Its derivative is what? 4x minus 3. And of course, since we need the 8x here, so we need to multiply this by 2 to produce the 8x. But this will give us what? 8x minus 6. But in this numerator, we only have 8x minus 5. So minus 6, in that case, we need to add a constant 1. Okay, so that when we add these two fractions, we'll get the original fraction, which is 8x minus 5 all over this denominator. So to evaluate the first integral, we just use u substitution. So this is just integral of 2 du over u, which is what? It is equal to 2 ln of absolute value of u. And then plus, to evaluate this integral, we evaluated this already, okay, in the previous examples. And this is just 2 over square root of 23 tangent inverse of the quantity 4x minus 3 all over square root of 23 plus c. And we can write our answer in this form without the absolute value, because this quadratic expression is always greater than 0. Okay, that's everything I have for you today. In my next video, I will give you some techniques that you can use to evaluate the other cases that we were not able to cover here. So don't forget to subscribe to my channel if you don't want to miss any of my videos. As always, thanks for watching and hope to see you next time. Bye bye.